Okay, so in the second part of this class, we're going to be looking into cross-validation. What do we exactly mean by cross-validation? So a lot of people use this term and it can mean two different things. So let's first clarify that, right? So there's when you hear about cross-validation, there's some folks who might be talking about how to adjust the parameters of a model, right? So imagine that you have, I don't know, you're working with a support vector machine, right? And as we've seen, depending on the kernel that we choose, there's going to be certain parameters that we need to adjust, right? And so in this case, what cross-validation does, it's basically let's say like a tiny part of your training data that's going to be used to adjust the parameters of the kernel or of whatever classifier you're working with, okay? So that's one possible scenario where cross-validation dataset is used, and it would mostly mean, again, a subset of your training dataset. And then on the other hand, we also talk about cross-validation when we talk about performance estimation, right? So, I mean, this is something that, again, you've been doing informally throughout this course. You've been dividing your data set into 70% for training and 30% for testing, or 80-20, right? Some of you have been working with folds. And so those things that you've been doing informally are things that we're going to see now formally, how they work and why are they defined like that, okay? But in terms of, again, performance estimation, what cross-validation refers to is basically on how the data set is divided into training and testing so that we can train the model and test the performance of the model on the testing data set.
In today's class, we will be focusing on cross-validation as performance estimation, and we will basically be looking into different techniques on how to divide datasets into training and testing depending on the nature of the data that we have.
There are two types of cross-validation methods. Exhaustive methods basically evaluate all the different possible combinations of dividing, a data set into training and testing, and then the non-exhaustive, which basically are used when we have really large data sets, and we can just simply not consider all the different possible combinations, and so in that case we use non-exhaustive cross-validation techniques to basically assess how to divide the data set. So today we're going to be seeing, in terms of exhaustive cross-validation techniques, we'll see a couple of them: leave one out cross-validation and leave P out cross-validation. And then for the non-exhaustive ones, we'll see k-fold cross-validation, random subsampling, and data split. Leave one out cross-validation. So this is an exhaustive technique. So it means that we typically use it when our data sets are not huge. And so basically, imagine that we have a data set with n samples, being n not super large. The way leave one out cross-validation works is that the training data set is defined as n minus 1. Okay, so your training data set is going to be all your data set minus one sample, and then you're going to test on that one. Okay, but the trick here is that, of course, you cannot just test on one sample. The trick here is that if you repeat this process n times, you're going to be training with n minus 1 different combinations of samples, and you're going to be testing basically on all the individual samples that you have in your data set. And so, you divide into n minus 1, test on one, but do that n times, and basically, the final true error used for the measure of the accuracy, it's basically the average error rate across all the different testing scenarios that we have covered, right? And again, we have covered n different testing scenarios, okay? And so basically the error will be the average across all those n cases. Similarly, leave P out cross-validation is very similar to leave one out, but rather than one, we leave out P. So basically we train with n minus P samples, we train our model, and we test with the remaining P. And we repeat this process as many times as possible, okay? And that many times as possible is basically the combinations of the n elements that we have in groups of P, okay? That's the number of times that we repeat this training and testing. And again, the errors that are reported are averaged across all the times we've repeated this. When our data sets are larger, there is no way that we can cover all the different combinations and basically of training and testing samples. And so we start to be a little bit more creative and original and basically consider alternative ways of dividing our data set. So k-fold cross-validation, what k-fold does is that it divides the data set into k-folds. Okay, it uses k minus 1 folds for the training, and the last fold, the remaining fold, is used for the testing. Mhm. As you can imagine here again, I mean, we are going to repeat this process in such a way that we explore basically all the different folds that we can explore in terms of training and testing. Okay, and again, the error that we report here is basically an averaged error across all the runs that we consider. I mean, again, this is fairly similar to what leave one out cross validation would look like, but in this case, we are talking in terms of folds. Okay, so we leave out one fold. Could be another way of looking into this. Now, for k-fold cross-validation, oftentimes, there's a question of how many folds should I consider. So, short answer is a common choice is 10. Okay. So you will see across the literature that oftentimes tenfold cross-validation is one of the heavily used options, right? In general, it's important to consider that when you work with a large number of folds, of course, that's going to require much more computational time, okay? Because you are considering many more folds. In fact, as you consider more folds, the variance in the error is going to be larger, right? Because I mean, if you consider more folds, the changes in the error are going to be definitely larger. But at the same time, the true error that you will get is small because we are exploring a lot of different possibilities. On the other hand, if you move more towards a smaller number of folds, the opposite is exactly going to happen, right? So I mean, you have a smaller computation. I mean, the computation is reduced, which is good. And the variance is going to be of the true error is also going to be small because in fact we are considering a small number of folds. But as a result of that small number, we will see that the bias of the estimator itself is also going to be really large. Okay, so the true error rates that we're going to be looking into can be much larger than when we consider a larger number of folds. And in general, as I was saying before, so large data sets, threefold cross-validation is considered to be sufficiently good. Typically k-fold, like k equals 10, tenfold cross-validation is very typical. And so oftentimes, I mean, what you can do is try with different folds and try and see, how the number of folds that you use might change the performance results of your classifier. Another of the non-exhaustive cross-validation techniques that we're going to be looking into is called random subsampling. Okay, and so basically the way this works is that for each run that we consider, we are going to randomly select a fixed number of samples, of data points, okay, without replacement, meaning that once we select a data point, we cannot select it again. And the data points that we select are the ones that are going to be part of our testing set, of our testing data set, right? If we repeat this this random split multiple times, we basically have different settings where we have, different samples for training and for testing. The last non-exhaustive cross-validation method that we are going to see today is data split, and it's probably the one that you are most familiar with because we have already been using in many examples throughout this course. Data split is generally used when we have a really large data set, and the way it works is that we divide the data set into training and testing sets with different percentages. So it could be 80-20, 70-30, 60-40, where the largest number always corresponds to the size of the training data set, and the smaller number always corresponds to the size of the testing data set. And very importantly, the samples that we select, randomly select for the training or testing sets are samples without replacement, meaning that once you randomly select one data point to be part of the training data set, it's never going to be used as part of the testing data set. And obviously that's what we pursue. Basically, we want to have two completely separated training and testing data sets that are going to be used, one for training and the other one for testing, making sure that the testing samples have not been used during training.